Okay, we have some students that are going to be taking the PSAT today, so I'm going to record this meeting for them, and they can view it later. It's always best to start with the learning targets that the textbook provides us. So these learning targets come from the textbook. And earlier in the week on Monday, we compared and contrasted Democritus, Dalton, and Lavoisier with Aristotle, Plato, and Empedocles. So today we're going to continue on that. We're going to look at Dalton. Dalton did other things besides the law of definite proportions and the law of multiple proportions. If you remember, the law of definite proportions says what? What does the law of definite proportions say? Do you remember that? Anybody remember that in the chat? Law of definite proportions. So I'm recording this because of the students taking the PSAT today. If you remember, the law of definite proportions says that water is always water. So water is always water. And the law of multiple proportions says that CO2 can differ from CO. So carbon monoxide is different from carbon dioxide. Your car has a catalytic converter on it, which is in the muffler. And what it does, it prevents the engine from making carbon monoxide because it's not good for plants. So the platinum in there in the catalytic converter, it's just basically platinum, which makes it very expensive. So if your ozone sensor goes out on your car, you need to replace those because it regulates the flow of oxygen into the engine. And the amount of oxygen will eat up the platinum in your catalytic converter. So if your ozone sensors go out, you must replace them or you're going to have a very expensive bill coming when your catalytic converter goes out. But the point here is that carbon monoxide and carbon dioxide in the law of multiple proportions have to be whole number ratios. And this is what relates to this second learning target in the textbook. It says, understand how Dalton's theory explains the conservation of mass. So if you remember, if you have, let's say, hydrogen and oxygen, you're making water, then you have to have whole number ratios of that. That is, the reactants have to equal the products. You're not going to lose half of hydrogen from the reactant to the product. Now, Dalton created his first table, and we showed that to you on Monday, and it's on the stream here. So you can see Dalton's first table. So Dalton did progress with his tables as he continued his research. So he published another table in 1805. And in this table, you can see he's also got numbers to the side here. And these are basically atomic weight values. So how did they do this? Well, they took water. They started with water. That's what Lavoisier was working with. And they separated it into hydrogen and oxygen. And then they took the amount of hydrogen made from the separation and they measured it. And they came up with a weight. And they compared that to the weight of oxygen. So based on Lavoisier's law of conservation of mass, if I started with 10 grams of water, then I should have, let's say, 8 grams, around 8.9 grams of oxygen and around 1.1 gram of hydrogen. Hydrogen is about 11% in water. So if you look at the content of water, water's H2O, there's 2 hydrogens. Hydrogen has a mass of 1, so it's 2 grams, plus oxygen, which is 16 grams, and you add 16 plus 2 is 18. Then you take the mass of hydrogen, 2 divided by 18. So 2 divided by 18 is around 11%. So water is around 11% hydrogen. So that's where I'm getting those numbers. So if you took 10 grams of it, right, and you separated it, around 1.1 grams should be hydrogen and around 8.9 grams should be oxygen. So they were doing this in the lab. They were trying to, this is going back to our learning target. It said, how does Dalton's theory relate to the conservation of mass? And that's what we're explaining to you here. That if you take 10 grams of water and you separate it, into those two gases, oxygen and hydrogen. You have them in a container, and then you measure that mass of the gas. So this is where he's getting those values right here. What they didn't know in 1805, they did not know that water was H2O. They just knew that it was hydrogen and oxygen. They knew there were two gases there. They didn't know the formula H2O. And that's how you can see his table changes from, it says here, Dalton's first table published below can be observed compared to his 1808 table. His first table records by mass of water to be 6.5 composed of hydrogen, and then it says the mass of water is 6.5. So if you go down here, we see water. Yeah, we see water 6.5, right? Everybody see that? So they started with 6.5. So instead of 10, they started with 6.5. Does everybody see that? That's the point. And then of that, it was 5.5 oxygen and then 1 part hydrogen. So if you took 1 divided by 5.5, you'll see that it's around 15%, I believe. So remember, our total there for water is 6.5. So we take our 1 divided by 6.5 times 100. So this is saying it's around 15%. So in his analysis, remember, his equipment wasn't that great. His analysis is saying here that hydrogen is 15% of water. And if we go back to our periodic table and we take 16, which is the mass of oxygen, plus 2, which is there's 2 hydrogens, you have 18. So you take 2 divided by 18 equals 0.11. So times 100 is 11%. So in water, this is a review from chapter 1. We're talking about percent composition. So water is around 11% hydrogen. And they're off a little bit here. He's saying it's around 15%. So we take our 1, once again, because it's 1 part 1 divided by 6.5 times 100. So there, he's saying there it's around 15%. So there's a little bit of error there. And I'm showing you this because I don't want you to think that they got all the numbers at the beginning correct and it was really smooth. This was a lot of trial and error. It took time to get the actual numbers to where they are today correctly on the periodic table. That's the point we want to make to you today with this. All right, so continuing on with our notes. So last week we introduced the cathode ray tube, or not last week, earlier in the week, sorry, on Monday, the cathode ray tube. And it says here that a typical cathode ray tube used by research for studying the relationship between mass and charge is illustrated in figure 4.6. I'm not really sure who developed the cathode ray tube. The book doesn't tell us here. A lot of different researchers were using it. And a big development, one of the big developments that came from the cathode ray tube, if you remember reading on Monday, we talked about the various methods that we can use to analyze atoms. We read that right here. We talked about the scanning tunneling microscope. So we had somebody read about that. And we mentioned also about the X-rays. Well, X-rays, if you went back to like 1895, that's when they were discovered. So my great-great-grandfather, they didn't have access to X-rays. X-rays were discovered in 1895 with the cathode ray tube. So let's get somebody to read here for us. Somebody read this right here. Get somebody to read that for us.
I can.
Okay, go ahead.
On November 8th, 1895, Röntgen noticed that when he shielded the cathode ray tube with a heavy black cardboard, the green fluorescent light caused a platinum screen 9 feet away to glow. Too far away to be reacting to the cathode rays as he understood them.
Okay, very good. So there's a little video attached with this. This was a huge breakthrough. Okay, so this screen back here is very significant. This was covered with like barium, which is a product of some rocks. So some rocks are effervescents, that is, they illuminate in the presence of like light. So if you're out collecting rocks and and you take them back and you're just messing with them with light and they glow in the dark, right? It's kind of interesting. So that's what happened here. And further study of these rocks leads to our next topic later on in the book. But this screen right here played a big role in our further understanding of the actual atom and other experiments that were done with the atom. So if we didn't know about rocks that were like fluorescent, like what he's talking about here with this barium, this came from rock. So let me play that again one more time for you. Okay, so that product was the result of from a rock. That you have to remember also, I mentioned earlier that helium, you don't get helium out of the atmosphere, you get it from rocks, and then you react it with various chemicals and you produce helium gas that we sell to, let's say, Kroger and medical supply places. All right, so continuing on with that. On Monday, we talked about the importance of magnets, right? That they make magic possible. So if you were paying attention to the news, the iPhone 12 just came out. Now, how is the iPhone 12 charged? Does anybody know how the iPhone 12 is charged in the chat? Tell me. How is the iPhone 12 charged? Do you plug it in? No, you don't plug it in. Now, the iPhone 10, you can plug in, but you can also charge it wirelessly. Has anybody ever heard of wireless charging? Yes or no? In the chat. Okay, so you've heard of wireless charging. The thinking in the future is that like TVs will be wireless. I mean, you can already see it now a little bit with cable. And the internet is really starting to cut cable. You have smart TVs now that you don't need cable connected to them. You can have your wireless modem in your house, and it'll connect to your smart TV, so you don't need a cable to connect that. If you didn't know that, most of you probably already have that. So the thinking is in the future that TVs will also be, you'll be able to turn them on without having them plugged into the electrical outlet. They'll be wireless as well, of wireless charging. That will probably come in the next 10 or 15 years. So how does anybody know how wireless charging works? So it goes back to the magnet. And I'm hitting on this because it's the magnet is what allows it to happen. It's not radio waves. If it was radio waves, you wouldn't be able to charge the battery. Radio waves are actually photons. They're not electrons. So radio waves goes back to, let's say, solar power. And radio waves are actually less powerful than visible light. So you would not be able to turn you wouldn't be able to turn this calculator on with radio waves. So you have to have a charging station that you plug into, and then the phone actually sets on the wireless charger. And so what's happening here is that there's a magnet. It says Apple's latest technology magnets. They're using a better magnet at the center of the phone to help the actual charging process. But once again, I am showing you the significance of magnets and how such a huge role they have played in our everyday life. Everything from the computer, the 0 and 1 on your coding is associated with the magnet. The North Pole, the positive going in the north direction would be the 0. And then let's say you flip it, where the positive is in the South Pole, that's a 1. So how the magnet is orientated tells you the 0 and 1 in code. So you have just lots of magnets in your computer that allow memory to occur. So magnets are associated with memory. They're also associated with generating electricity. And on Monday, we discussed, what did the magnet help us prove? Can anybody tell us in the chat, what did the magnet help us prove? We discussed it on Monday. What did the magnet help us prove? So the magnet helped us prove the what? Helped us prove what? What did the magnet help us prove? Okay, so the magnet helped us prove the first model of the atom. This is the first model. If you remember, Dalton did propose a model of the atom. And what did he base it on? We talked about this Monday. What did Dalton base his model of the atom on?
Plum pudding.
Right, billiard balls. Thank you, Anna. So if we went back and I showed you Dalton's list, his initial list, he had those circles and he had various symbols in them. So his model was a circular atomic model, which he did not have any experiment to justify it. So the first model of an atom based on an experiment justifying a thing in the atom was from the actual magnet. So Thomson is saying that there are electrons in the structure of the atom based on a magnet. So what he did, he took the magnet and he moved it over the cathode rays, and the magnet interfered with the cathode ray. So because the magnet is independent of itself, it must have those same things inside of it. The magnet by itself, it must have those cathode rays inside of it in its structure somehow. So he didn't know how they were structured, but the magnet played a role. It played such an enormous role in our development of the actual atom. So if we didn't have the magnet, we wouldn't even have our first model of the atom. It wouldn't have led to further curiosity about, so we know this is there, how is it arranged? So the magnet played just an enormous role in our understanding of the actual atom. So if we go back to our other videos. Now, in the textbook, I really should go to the textbook first before we play a couple of these videos. And let's read a little bit more. So we talked about the cathode ray, and we talked about how Roentgen, I think that's how you say it's German, he discovered the X-ray. He by accident, he was trying to shield the cathode rays, and by accident, he discovered this property. And when he discovered it, what's very interesting about him, he did not patent it because he wanted it to be used for medical purposes. People noticed that you could look at like people's bones and determine whether they were broken or not. So it had a big impact on the medical community. Imagine just being in an accident and not knowing whether your hand is broken, the bit difference that the x-ray would make. So continuing on with this. Well, let's go ahead and read it. This is what the next video discusses. So let's read this right here. Somebody read this for us? This paragraph.
I can.
Go ahead.
In spite of the progress made from all of the cathode ray tube experiments, no one succeeded in determining the mass of a single cathode ray particle. Unable to measure the particle's mass directly, English physicist J.J. Thomson began a series of cathode ray tube experiments at Cambridge University in the late 1890s to determine the ratio of its charge to its mass.
Okay, so that's the video I'm going to show you here in a minute. So they couldn't figure out the mass, right? The single mass. So they're like, let's look at it from a density. Let's see if we can't find the density or the charge to mass ratio, which is a ratio just like density is, of the electron. And then maybe somebody else will come along and figure out the actual charge of the electron. So let's read here. You can read that for us.
I can.
Go ahead.
By carefully measuring the effects of both magnetic and electric fields on a cathode ray, Thomson was able to determine the charge to mass ratio of the charged particle. He then compared the ratio to other known ratios.
Okay. So this goes on to basically discuss what he concludes. Thomson concluded that the mass of the charged particle was much less than that of a hydrogen atom, the lightest known atom. So I'm going to show you the video that explains it a little bit better, and there's some math associated with it. But before I do that, I'm going to show you two videos. I'm going to show you the charge to mass ratio that Thomson did, and then Millikin. Millikin was an American physicist. So let's read right about here. Somebody read that for us. Get somebody to read that, please.
I can.
Thank you.
The next significant development came from the early 1910s when the American physicist Robert Millikin determined the charge of an electron using the oil drop apparatus shown in figure 4.8. In this apparatus, oil is sprayed into the chamber above the two parallel charged plates.
Okay, so this happened about 110 years ago. This is not too long ago, 1910s. So my grandfather, he was still alive at that time. All right, so we have Millikin, he's determining the charge of an electron. And you can see it right here. I'm going to show you the video. It's kind of cooler to see it in action. So we go on and we read right here. Let's read this right here. You can read this for us.
I'll read it.
Okay, go ahead.
Knowing the electron's charge and using the known to charge to mass ratio, Millikan calculated the mass of an electron. The equation below shows how small the mass of an electron is.
Okay, very good. My point to you is the textbook doesn't show you the math of how they actually calculated the mass of an electron. They just show it to you right here. right? This is mass of an electron right here. How they did it is just like with density. If you have density equals mass over volume, right? You have density equals mass divided by volume. If you know three of these, if you know two of the three variables, you can solve for the unknown. And that's what's going on. They're not showing you in the textbook how they did it, but once again, they're using Millikin's charge. He's the one that calculated the mass of an electron. He's the one who is credited with this. He did not put it on a scale. What he did, he calculated the charge of the electron in his Millikin oil drop apparatus. And from that, he used Thomson's charge to mass ratio, and he was able to solve for the mass. So Thomson really did a better job of defining mass and the charge to mass ratio. Is everybody clear? They're not showing you the math here. So the technical part is really shown in Thomson's analysis. So this right here, where is this one? Yeah, this one gets into a little bit of math. So let's watch this. This is pretty good.
Which is handled by some fluorescent material, such that the beam after striking the mirror appearing on one spot. The same is recorded in mirror to measure the difference of the beam. Though there is no electrical or magnetic field, the beam traveling in a straight line and there is no difference. The wire passes between two parallel aluminum plates. When they are connected to a vacuum, the beam experiences an electric field in this direction and experience of force in the opposite direction. The magnitude of this force is given by F E, where E is the magnitude of the electrical field and small e is the quantity of charge of the electron. The magnetic is shown, the beam experiences a magnetic field in this direction. And the direction of motion of the charged particle is this. According to the Fleming's left-hand rule, the negatively charged particle experiences a force in this direction. The magnitude of force is given by F equal to EVH. Fh is the force experienced by the charge in the magnetic field. E is the quantity of charge, V is the velocity, and H is the magnitude of magnetic field. Both electrical and magnetic fields are applied simultaneously. Tested in such a manner that these two forces cancel out each other. This is achieved in what now is zero electricity. At this case, F is equal to Fh, or E into Q equal to E into Ph, or V equal to electrovoltage. The magnet is removed such that the force on the electron is electric field. In this situation, now the force is not equal to E and the however, the whole force around this charge is a magnetic field, but the problem is the same as that of a projectile in a magnetic field. This direction there is no force. Then we have no constant velocity. Now V equal to E divided by H. Thus, basically Faraday is X equal to V. It's equal to E divided by H. That is the equation of the mass. In the other direction, there is a mass F E equal to E. And the mass is equal to F E divided by F, which is equal to E divided by F. Therefore, y equal to half mc squared, where A is the acceleration. Therefore, y equal to half E divided by mc squared. Now we get G equal to X into H divided by E of y. Substituting in this equation, we get y equal to E by 2m x h by E whole square, which implies E by m equal to 2y E divided by x square h square. Now in this equation, the magnitude of electric field, the magnitude of magnetic field y and x are known quantities. The experimental results, we get E divided by m equal to 1.7588196 into 10 to the power 11 joules per kg.
Okay, so with that said, my question for you in the chat, tell me, where is the mass coming from? How is he calculating the mass in this experiment? One word starts with an F. Anybody? What is he using to calculate the mass? One word starts with an F. If you were paying attention, you probably heard him say it. No? In physics, you're going to study this next year. It's the foundation of Isaac Newton. So if you study almost all the physics you will see will be classical mechanics, which is the study of Newton's 3 laws. And if you continue to pursue physics, you'll see a little bit of Einstein with the quantum mechanics. So Newton's second law is associated with force. And what does force equal? Does anybody know what force equals? If you were listening to the video, he talked about the force applied. All right. So when you apply a force equals what? I know what force equals? So force equals mass times acceleration. So from this, you can then determine the mass in your actual last unit. So the important thing to focus on are the last units here. You see he has kilogram there? So it's charge to mass ratio. That is coming from the force. So he's just crossing out to where he's got the mass in the unit there from the original. Like if you have force equals mass times acceleration, you get the force, you got the acceleration, you can solve for mass, which is exactly what he's doing right here. Coulomb, that's the charge. So the next one is Millikin. This is gentleman, American, 1910.
Physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, Millikin looked to determine the charge of the electrons. That he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikin's Wire experiment. Using this method, he calculated that the charge of an electron was about 1.6 times 10 to the power negative 19 electrons.
Okay, so once again, you can see the math that they're showing you here. Actually, they actually calculate the mass of the electron. So this was Thomson's value here. E over m, that's the mass. See that kilogram right there? Coulombs per kilogram? This was calculated by Thomson. And this was calculated by Millikin. So when you divide these two, you get the mass of the electron. This is no different than I was mentioned to you before. This would be like density, and you have mass and volume. It's a similar idea. If you have three different variables, you can solve for the unknown, which is the goal. So they never really, put the electron on a scale and measured it. They just solved for the other variables and then isolated m. This is important to see right here. Any question on that? You can watch the video again if you need to see it again. Before I X out on this, what Millikin did was enormous. Not only did he solve for the mass of an electron, it is very important to know the charge of a single electron. This right here has enormous significance as far as counting things. If you know the mass of a single electron, you can start to count things, right? So that's what we started to do. We started to count things with that. And you can see this right here. So let's read on in our notes here. These are notes from various places. Let's get somebody to read this here. Can somebody read that for us? It's about Millikin. Kind of reiterates what was just discussed on the film. Somebody read that for us? Can you see that? Somebody?
I can read it, but do I read the big numbers?
No, you can just say 9 and then continue,
Okay.
Or whatever number it is. Yeah.
Okay.
Which number?
Accurate determinations of Avogadro's number require the measurement of a single quantity on both the atomic and macroscopic scales using the same unit of measurement. This became possible for the first time when American physicist Robert Millikin measured the charge of an electron. The charge sorry, it's really blurry. The charge on something of electrons has been known for some time and is the constant called the Faraday something. Okay. The best estimate of the value of according to the National Institute of Standards and Technology, is 9 coulombs per mole of electrons. The best estimate of the charge on an electron based on modern experiment is 1 × 10⁻19 coulomb per electron.
Okay, so they introduced Faraday up here, right? So Faraday is a constant. And what they did, they took silver, right? So they took silver as a compound. So if you can make silver-plated jewelry, you can make gold-plated jewelry. Does everybody know that? So in the chat, just say, I know you can make plated jewelry or gold-plated jewelry. Yes or no? Okay, great. That's what's going on here. If you you can dissolve gold. Most gold is mined and then it's dissolved into like a powder and then it's reassembled. If you look at the manufacturing of gold, the process, they use a lot of chemicals to do that. So what's happening here, they have dissolved silver into, let's say, silver chloride, right? So in a liquid, you have silver floating around as an ion. And they're going to run electricity through it, through this ion, making silver-plated metal. So they run electricity through a solution. It says the value of F, Faraday's constant, was determined by weighing the amount of silver deposited in an electrochemical reaction. So the question is, well, how much did they weigh? right? So how did they know where to stop? And that goes back to the periodic table. By this time, you're talking around 1910, they had a fairly good periodic table. So if you just Google like 1910 periodic table, you can find then like the mass of the silver. That was the stopping point. So you find silver on the periodic table, Ag right here. That's the atomic number. It's not showing the mass there, but that's where they're getting that number. So silver right here, that's where they're getting the number to stop. So if you're putting silver, or like you're plating it and you have the mass before you plate it, and then you have the mass after, that's where you know to stop. So what does that mean? It goes back to what the Faraday constant is, right? So if you know that the mass of silver is associated with a set amount, every atom has a set mass, right? Associated with its number of protons, its number of neutrons. That's what the mass is. And every element increases in mass. So there's a pattern there. So if you stop the electrical current right at the mass of silver being produced, you've counted the number of silver atoms inside that mass. Is everybody clear? That's how we counted the mole. So when you hear like 6.02 times 10 to the 23rd, we talked about it. Mentioned it before, like a dozen is a name that represents a number. A dozen is 12. That's a name, a dozen, represents 12. Well, the mole represents a number. It represents 602 sextillion, or 6.02 times 10 to the 23rd. It's this huge number. And if we were all counting on the Earth 1,000 a second, it would take like 3,000 years to count to that number. That's how big that number is. So it's not humanly possible to count the silver atoms in the mass of silver on the periodic table. So the mass on the 1910 periodic table, that's where they stopped. So it says here, by weighing the amount of silver deposited. Well, how did they know when to stop? The periodic table told them. Because the mole is based on the mass of every element on the periodic table. So if you measure out 12 grams of copper, it's a mole. So only really one thing was counted. That was silver. And they took that charge to make the silver, and they divided it by one electron. So if you have a total charge it takes to make, let's say, the mass of silver. Let's go to the periodic table. Up here, we'll see it. I don't see it very clearly there, so I need to get into the periodic table. Let's see, this one looks like it has it there. I need to blow it up a little bit. I don't have it memorized. Mass there. Go up there a little bit. Looks like around 108. That's not blowing up very well. We can just Google the mass of silver. Thing to do. All right, so they stopped at 108. So the point here, it's where we're concluding today, is that Millikin, his experiment had not only calculated the mass of the electron, but it also enabled us to count the elements. That is, we took silver and we counted how many atoms were in 107 grams. We took it, that's where we stopped. They were making 107 grams is a lot. That's a fairly large mass. 454 grams is a pound. So you're talking about, almost, let's say, a quarter of a pound there. That is a significant mass. So they counted a quarter of a pound of silver. And that's where the Faraday constant comes from. It's a fairly large amount of energy. Is everybody clear here? This is a good chunk of energy because you're talking about a quarter of a pound of silver. It was counted. And then they took the charge of a single electron, divided it by this, and they got the number of moles. That is the number of silver atoms there. So that's how they counted the elements, or the number of atoms inside the mass on the periodic table. This is, you'll see this again throughout the chapter. We'll reiterate this again next week. This is where we'll start. So if you have any questions, we'll address it again. You usually have to hear this more than once to see as far as the significance of this. If things can be counted, then you can prevent errors. You can prevent cheating is the big thing. If you don't count things correctly, people will steal from you. So if anybody has any questions, you may ask. One thing to you. There is power that was assigned. All we want you to do is read that. It's part of Wicker. So when you read it, I give you credit. It's basically saying, okay, that you read something out of the textbook. It's hard to assign the textbook to read is the point of their assigning that. So they assigned it as a possible assignment. So I just went ahead and assigned it to you. So please do that. And then next week, we will discuss a little bit in more detail the egg drop as well. But with that said, if you have any questions, I thank you for showing up, and I'll see you next week.